Hi, this is Kenny Lee, and in this video we're going to talk about thermodynamics. We're going to talk about the laws and the terms and how they apply a little bit. We'll get into the actual math and calculations in another time. Let's start off with the zeroth law of thermodynamics. Yes, there's a zero law. That's because we came up with the others and found out we forgot something, which basically says if one object is in thermal equilibrium with another object, and a third object in thermal equilibrium with one of those objects, then the other two are also in thermal equilibrium. Which basically means if two things are in thermal equilibrium with each other, and then one of those things is in thermal equilibrium with a third object, then these two are also in thermal equilibrium. Basically, thermal equilibrium is when there is no net movement of heat between the two objects. What one object gives, it also gets back. And so there's no movement of energy there. So in order for heat to flow, the two objects have to be at different temperatures. And heat always flows from high temperature to low temperature. Now comes the first law of thermodynamics. This is basically the law of conservation of energy, just with a little added caveats for internal energy, basically. So basically, that the energy of a isolated system has to stay the same. Now, there's actually three different types of systems we'll talk about. Isolated system, that's where there's no energy, no matter exchanged to the surroundings. So everything's self-contained. A closed system is where the matter is contained, but energy can flow in and out of the system. An open system is pretty much anything goes. Energy and matter can flow in and out of the system. So what does this give us? Well, we have some equations that we got to play with on this one. So we got this one. Work equals minus P delta V, and V is volume in this case. Now this is from the point of view of the gas inside the piston. A lot of times in physics, we don't have the negative sign there because we use the point of view of the piston itself. But in AP2 and a lot of chemistry, this is their definition of work because they're interested in the gas that's inside that's being compressed or expanded. Likewise, this is also written in a way for the perspective of the gas that's on the inside. Otherwise, and if you're doing it from the piston, that will be a minus sign. But basically, W is work, P is pressure, V is volume, U is the internal energy. So delta U, remember, it's always final minus original, or initial. Q stands for heat, okay? And we got some terms for different processes in thermodynamics. So isovolumetric or isochoric, you don't see it as much referred to as that anymore, but it's still pretty popular. Anymore, they're trying to convert it to isovolumetric because it simply makes more sense. It means that it stays the same volume. Iso means the same. And so delta V is 0. So if delta V is 0, then that means work is 0. If work is 0, that means the change in internal energy has to do with the heat. And it represents a vertical line on a pressure volume diagram, which we'll get into later. Isobaric means same pressure. So it's represented as a horizontal line on a pressure volume diagram. And that's where pressure stays the same, but the volume can increase or decrease depending on what's being done or what's going on. Isothermal means the same temperature. So if there's no change in temperature or internal energy, on a pressure volume diagram, it kind of looks like this. It's more of a 1 over R relationship, where the temperature stays the same, although the pressure and volume will change along that line. So if the temperature doesn't change, the internal energy also doesn't change. So if the internal energy is 0, that means work is equal to the heat from the system. Adiabatic It's adiabatic, not adiabatic. That means no energy is transferred to the environment or the surroundings in that process. And so that means there's no heat given off or taken in. So that means Q is 0. So if Q is 0, then internal energy has to do with, or change in internal energy, has to do with the work done. Then an isolated system, no heat or work is done with the surroundings. So that means Q is equal to W, which is equal to 0. So that means the internal energy does not change. It stays the same. And for adiabatic function on a pressure volume diagram, it's more steep. It kind of does more something like this. So if you see something like that, and it's different from this one. This one's nice 1 over R relationship. This is more kind of a sharp motion and turn. And usually they about have to tell you what that is because it's very hard to tell it from any other process that changes both pressure and volume. Getting back to what I referred to earlier is that this equation is with the perspective of the gas on the inside of the piston or whatever. And because of that, we've got some things we need to consider. If the volume decreases, okay, so the volume decreases, that means the gas is being compressed. So that means work is being done on the gas. So the volume will go down. So delta V is the final volume minus the initial volume. So as we compress it, this in turn ends up being negative. Well, if that's negative, a negative times another negative makes a positive. So that's positive work being done on the gas by the piston. From the piston's point of view, it's doing work. So it's giving up that work. It's doing something. So it's losing that work. So it kind of depends on if we're looking at the point of view of the gas or the piston, what we call positive and negative. It's always better to pick one point of view and stick with it whenever possible. That way you don't confuse yourself. So if we look at this, that's positive if it's work done on the system or on the gas by the environment, which is the piston. Negative if work is being done by the system, in other words, the gas on the environment. So let's say the gas is expanding and pushes the piston out. Well, that means the gas has to be doing something. It's giving up some work to push that piston back, and the piston's gaining that. Same thing with heat. Positive if heat is added to the system by the environment. Negative if heat is taken from the gas and put into the environment. So if I compress a gas, usually that gas will heat up. Okay, and so that means we're adding heat to that gas by doing that. If the gas is allowed to expand, for the gas, that's a cooling process, so it's giving up heat to the environment. And we'll look at this more when we get into pressure volume diagrams and such. But that's just an idea to kind of keep you or get you started on this. The second law of thermodynamics says no energy transfer is 100% efficient. That means you're going to get some loss. And that lost heat, we call it entropy. Sometimes we call it waste heat, unusable energy, or measure of disorder of the system. But we can figure out the efficiency of a process one of three different ways. All these are very similar. So basically, E is for efficiency as a percentage. And if we take the work divided by the heat given off during the high temperature phase of the reaction or the process, that could be the efficiency. Or if the heat given off during the high temperature part of the process versus the heat from the cooling or low temperature part of the process divided by that temperature from the high process, we can do that and also get the efficiency. Or if we can go by temperature, the temperature sustained during the high temperature part of the process versus the temperature for the cooling part divided by the temperature from the high temperature process can also give you the efficiency. But that's just usually a simple calculation, usually with a motor or some type of other process where you got a kind of a loop on a pressure volume diagram You can figure out the efficiency going on by this process. The third law of thermodynamics is, well, I'm going to paraphrase it. It's as the temperature decreases of a substance, the molecular motion gets less and less and less. So that means it's giving off less energy to the environment because it's having fewer interactions with the environment for the molecules bumping into each other. And so at some point, this kind of becomes more of a constant as it approaches absolute zero. Now, absolute zero is when there's no molecular motion whatsoever. So the molecules in this paper, in this pen, in the ink, whatever, they're vibrating. But as we cool this to more and more towards absolute zero, they vibrate less and less and less. And if we theoretically get to absolute zero, they'll be kind of locked in place and they won't move at all. We can't really get there, but we can get to where there's just very slight movement. But anyway, those are the technically 4 laws of thermodynamics. The 3 different types of systems and 4 different types of processes that can happen through thermodynamics that we've given specific names to. And later on, we'll talk about pressure volume diagrams and how we can use those to solve problems using the ideal gas law. Thanks for watching. Tune in again for some more videos about physics. Goodbye.